Okay, Assalamualaikum and a good afternoon. Okay, today we are going to step in the second part of the fifth chapter, discussing the frequency response and Bode plot. Okay, in the second part, we are going to look at the transfer function and analyze the frequency response of a network. If you still remember, in the first part of the fifth chapter, we have derived the transfer function for a given network represented by a circuit, in which the transfer function basically showing the relation between the output and the input of the system. Okay, so from the transfer function, usually the transfer function represented as H in S domain is basically the ratio between the output divided by the input. Okay, so from this equation, from this transfer function, we can estimate what types of filter the system is, what's the cutoff frequency, what's the which part is the passband area and which part is the stopband area. So in this second part, we are going to illustrate the frequency response from the transfer function. Okay, for example, this is the transfer function. So we are going to plot how the system looks like, or the frequency response looks like. So from there we can identify what types of filter the system use, and other parameters such as the cutoff frequency, the passband frequency and stopband frequency. Okay, so we are going to use Bode plot to represent the frequency response of a circuit or a network. So I believe that you have learned the Bode plot in other courses. So basically, this can give you a quick recap on how to analyze a system by using Bode plot. So basically, the Bode plot approximates the frequency response of a circuit or a network using straight line approximation. Okay, and then it consists of two separate plots, which are the magnitude and the phase plots, and it is drawn on semi-log graph paper. Okay, it is not the same as normal graph paper. Okay, this is how the semi-log graph paper looks like. So as stated on top, it is semi-logarithmic paper. So if you compare with the normal graph paper, you can see that the sections is not equal in size. Okay, so you can see this one is a bit bigger compared to the next section. Okay, so basically the semi-log graph paper breaks the sections by decade. So you can see that this one, from the lighter, the white color to the darker green, represent a decade. Okay, and then followed by the next decade, and then next decade, and so on. Okay, so here you can see also the number from 1 to 10. Okay, for example, we have here is 0.1. So the next decade times 10, it will be 1. The next decade at this point times 10 is 10, and it is 100, and this is the 1000. Okay, and this is the omega. Okay, so in decade. So how about the subsection inside a decade? So if here is 0.1, here is 1, so here is 0.2, 0.3, up to 0.9, and then 1. Okay, in the next decade, 1 until 10, so each subsection represent 2, 3, until 9. Okay, this is for 2, this is for 3, 4, and so on. Okay, followed by the next decade, here is 10 until 100, so the subsection, then here is 20, 30 until 90, and so on. Okay, so but if you know, this is for the x-axis, and for the y-axis you may notice equivalent size. Okay, so you can basically put any values in. For example, here is 0, here is 10, 20, and so on, and the unit is in dB. Okay, in order to plot the plot, so the first thing is to derive a transfer function from the given system or from the given circuit. So after a partial fraction expansion and so on, so you'll be having an equation with a combination of constant, in this case represented by k. So this is the constant. And then components on top and at the bottom. Okay, so you have s outside the bracket, and then you have s inside the bracket as the numerator, and as at the bottom denominator you have a few components, s plus one value and then s plus the second value. Okay, so once you have the transfer function, so you need to rewrite the transfer function in standard form. Okay, so what does it mean by standard form? Meaning that you need to separate the transfer function into components. So it consists of two main components. The left hand side, I call it as a constant k naught, and then on the right hand side you have the s components equation. Okay, so in this case you can break this example into components. So the first one you have constant, so this is the constant part, so the first one you have k. Okay, and on the right hand side you have s outside the bracket, so this is s outside the bracket, and you have s plus z1 inside the bracket as numerator, and at denominator you have s plus p1 and s plus p2. So what does it mean by standard form? In standard form, you have to make sure all s equation inside the bracket being added by 1. So you need to remove z1 so that you have it being replaced by 1. So here it must be s plus 1. At this point it must be s plus 1. Okay, it cannot be s plus other values than 1. Therefore, in order to do that, you need to take out the z1. So in this case it will become, so this component will become z1. So now s divided by z1 plus 1. Okay, so for this particular component, so now you have the s equation plus 1. Okay, doesn't matter it being divided with any values as long as the s equation added by 1. Okay, so now on top the equation as the numerator become s z1 in the bracket s divided by z1 plus 1. Okay, so this is the s and this is from the component. Okay, so now other parameters than s must be considered as constant. So in this case s remain at that position, and S equation inside the bracket also remain at that position. So now the other parameters must be considered as constant. So now k z1. So you can remove the z1 from there. Okay, let's look at the denominator. So now you need to remove p1. Okay, so in this case, p1, so this equation become p1 s over p1 plus 1. Same goes to the second component. You have p2 s divided by p2 plus 1. Okay, so next, move all other parameters than s into constant values. So now you have p1, you remove this one, it become constant, and then you remove this one, it become constant. Okay, so now you already have constant equation k naught equal to k multiplied with z1 divided by p1 p2. Okay, so now you rewrite the equation into standard form. So this is the standard form. So if compare the one that we have derived on top with the bottom, so you have the constant, this is the k naught, k z1 divided by p1 p2, and numerator you have s outside the bracket and then s inside the bracket in standard form. So in standard form it is s divided by z1 plus 1. Same goes to the bottom part, denominator. So there's no s outside the brackets, only s inside two brackets. So s divided by p1, this one, plus 1, and s divided by p2 plus 1. So this is the equation in standard form. Okay, from this standard form equation, then you will plot all components. Okay, so you have the first component constant, and then you have s outside the bracket, you have s inside the bracket on top, and then you have s at the bottom and s at the bottom as another one. Okay, next, once you have the equation in standard form, so you can replace s with j omega. So it is not compulsory. Okay, s need to be replaced by j omega if you need to calculate the magnitude of the transfer function. So you replace all s with j omega, both the numerator and denominator. Okay, so once you have replaced the s with j omega, so you can convert the equation into polar form. Okay, so this is the constant k naught, and then you have j omega here. So you have the parameter, the magnitude is omega. As we have seen j in Fourier series chapter, j equal to 90 degree or pi over 2. Okay, so this is the first on top, and in the second part you have this equation in complex form or rectangular form, so you can convert the equation into polar form. So you have the magnitude for the first component and the phase. Same goes to the denominator. Next, you can calculate the magnitude or gain of the transfer function by calculating the logarithmic value of the magnitude. It is 20 log of the magnitude. All magnitudes involved in the component of your transfer function. Okay, and okay, so either you can multiply all the magnitude first and then multiply with 20 log 10, or you can calculate individual component or converting individual magnitude into dB and total them up. So same goes to the phase of the transfer function. So in order to plot the Bode plot, once you have the standard form equation, so you can identify how many components you have in your sketch or in your plot. Okay, so first we know that this is the constant k naught. Okay, so k naught will be in dB, so you can calculate k naught in dB equal to 20 log 10 of your k naught. So your k naught is kz1 divided by p1 p2. Okay, so this is the first component you have, followed by, look at the equation on top, the numerator. First, look at the s component outside the bracket. Okay, so in this case you have one s outside the bracket, so this is the first component. So the second component, you have s outside the bracket, so the equation, so the transfer function of the first component is h1s equal to s. So you have s outside the bracket, so you have h1s, and then you have the second component h2s, and then you have the third component h3s, and you have the fourth component h4s. Okay, next you have, okay, and h1s, when you have s outside the bracket, this is called zeros at origin. Okay, so all numerator, so all s on top is called zeros. Either it is at origin or not at origin. Okay, so if it is outside the bracket, so you have here is zeros at origin. Okay, so the third component, you have h2s equal to the equation s over z1 plus 1. So here, since it is numerator, so it is zeros at, it is not at origin, it is now at z1. Okay, move on to the fourth component. So it is h3s equal to, so since it is denominator, so the equation is at the bottom, so you need to, the transfer function for this specific component equal to s divided by p1 plus 1. So don't forget to represent 1 divided by this component, because this component is the denominator. And when the component is denominator, so all s is known as poles. Okay, so you have here is poles at p1. Okay, if you have s outside the bracket as denominator, so it is poles at origin. Okay, so lastly you have final component h4s or fifth h4s, so still at the bottom, so 1 over s divided by p2 plus 1. So in this case you have poles at p1. Okay, I'll show you in details in next slide. Okay, in more organized way, once we have the transfer functions, so identify how many components you have, whether it is poles or zeros at origin, not at origin. Okay, so identify how many components. So first you have the constant, next you have s outside the origin, this is zeros at origin, and you have the third component, and then you have the fourth one, poles at p1, and you have the fifth one. Okay, so what you need to do first, you need to write down the transfer function for each individual component. Okay, so start with the constant. So first you have h1s equal to 20 log of your k naught. In this case, 20 log 10 of k naught equal to kz1 divided by p1 p2. So you get this one equal to k0 in dB. Move on to the next second component. So complete the numerator part first. Okay, so second you have h2s. What's the equation? It is just a single s equal to s. So this is, you know, when s on top it is zeros and it is outside the bracket, so it is at origin. So what does it mean by origin? So origin in Bode plot is basically at omega equal to 1. This is the origin. Okay, it is not at 0. Okay, move on to the next numerator. So you have the third one, h3s equal to the equation s divided by z1 plus 1. So s on top, it is known as zeros, but now it is at z1 position, at z1. Okay, so you have considered all components on top. Now move on to the denominator part. So you have the fourth component, h4s. So don't forget denominator, it must be always at the bottom. So s divided by p1 plus 1. So when s at the bottom, it is poles. The location is at p1. Okay, finally the fifth component, you have h5s. Again, denominator part 1 over s divided by p2 plus 1. So again, you have another poles, but these poles located at p2 position. Okay, so in order to score or to get full marks in Bode plot, so it is recommended to list out all transfer function for individual components first before you proceed to the sketching of plot. Okay, once you have write down the transfer function for individual component, so now let's plot the frequency response for individual component. So the first one, just now we have the constant h1s equal to 20 log of your constant k. So you have k0 in dB. So therefore you plot in, you sketch when the question asks you to sketch, so you can just briefly sketch your answer. So in this case, don't forget the x-axis represented by omega, so it's separated in decade. So for example, you have here is 0.1, so here is 1, 10, 100 and so on. Okay, so if you have constant k, so it is plotted as constant values of k0 in dB, while the phase represented as 0 degree. Okay, remember when you have constant, it is a constant magnitude and phase. Okay. Okay, next, when you have zeros at origin, remember when you have h to s just now equal to s, when you have s outside the bracket on top in the numerator part, so it is zeros at origin. So in s also is known as j omega, so you can plot the as zeros at origin. Remember, origin in Bode plot when omega equal to 1, so you have positive slope passing through omega equal to 1. So what is positive slope? Is something like this, and it must cross at omega equal to 1. So omega equal to 1 is the origin in Bode plot by 20 dB per decade increment. Okay, meaning that you have the graph something like this. So for example, here is 0.1, so you have a decade, it's 1, 10 and so on. So the line positive slope so it's going up, crossing at 1. Okay, the line must crosses at 1 and increment by 20 dB per decade, meaning that, so the line crossing at 1, so it goes through all decades, but the increment per decade is 20. So here is minus 20, here is 0 in y-axis, and crosses at 1. So next decade by 20, and next decade again another 20, and so on. Okay, this is 20 dB per decade line, 20 dB per decade. Okay, so this is how the frequency response of zeros at origin looks like. Okay, so we have a line, this is minus 20 dB, and then 20 dB, and you have another one, so 0.1 here is 10. If you have 100 here, so another one, so here is 40. Okay, so positive slope by 20 dB per decade, crossing at 1. So while for the phase, if you have zeros at origin, the phase is always 90 degree, positive 90 degree. Okay, so don't forget to have separate plot for magnitude and phase. Okay, when you have zeros at origin, you have positive slope increment by 20 dB per decade and crossing at 1. But when you have poles at origin, poles, you know that the S will be at the bottom as denominator. So in this case, for example, you have HS equal to 1 over S. So S at the bottom, and it is outside the bracket. So this is poles at origin, meaning that you should have aligned, so poles negative slope, so zeros positive slope. Okay, so poles, the line going down, crossing at origin, so origin is 1, and the line, the trend is decrement by 20 dB per decade. So this line, next decade is 10, here is 0.1, so here is 20 dB, so the line decreased by 20 dB per decade. So 1 decade, so this is 1 decade, this is another decade, and so on. So that for each decade the line decreases by 20 dB. Okay, negative 20. Okay, so this is the poles at origin frequency response. Okay, while the phase for zeros at origin is always negative 90 degree, constant negative 90 degree. For zeros at origin, it is constant positive 90 degree. Okay, next move on to the next component on top. So when you have S inside the bracket, so it is zeros not at origin. So where is it? It is at Z1 in this case. So it is also known as real zeros at Z1. Same goes to the denominator part. You have S at the bottom, so it is poles not at origin. So you have one at P1 and the second one at P2. So this is also known as real poles at P1 and P2. Okay, let's look at when you have zeros at Z1, real zeros at Z1. So real zeros at Z1. Okay, so how the frequency response looks like. So it will be a constant line from 0 up to the Z1 value. Okay, up, it is constant 0 from the previous decade to Z1 value, and it will be having a positive slope 20 dB per decade from Z1 onwards. So here is 0, so for example Z1, so next decade is 10 times Z1, next decade is 100 times Z1, and so on. Okay, Okay, from Z1 onwards, you'll be having a positive 20 dB per decade lines from Z1 onwards. So here is 20 dB, here is 40 dB, and so on. Okay, this is for the magnitude plot of real zeros at Z1. Okay, if you have another zeros at Z2, for example, so you'll be having separate plot. So for example, if you have Hs equal to S over Z2 plus 1, so you know you have zeros at Z2, so plot another one. So you have 0 up to Z2. Okay, so this is the magnitude of Hs, and it will be positive 20 dB per decade slope from Z2 onwards. So here is 10 Z2 and so on. So the increment is 20 dB per decade. Okay, next for the phase plot of Z1. Okay, this is the phase plot. Okay, if you have zeros at Z1, so it will be having a 45 degree point in phase. Okay, just mark 45 degree point at that particular frequency, in this case Z1, and then you extend the line by 45 degree to the next decade and 45 degree to the previous decade. For example, you have Z1 here, so it must be 45 degree here. So the previous decade is 0.1 Z1, the next decade is 10 Z1. Okay, so from here you extend 45 degree to the next decade and extend downwards 45 degree to previous decade. Okay, so and the rest will be 0. Okay, so this is the phase response for zeros at Z1. Okay, for example, if you have for this one at Z2, okay, so phase for Z2. All right, so let's have the phase. So here is your Z2, and earlier decade is 0.1 Z2, next decade is 10 Z2. Okay, so for the phase plot, it must be 45 degree at that particular frequency, Z2 in this case, so 45 degree. So extend the line to another 45 degree down, and to the next decade 45 degree up. So here is 90, so this is the next decade. Okay, so this is the phase response for Z2, and don't forget to extend constant value from the maximum 90 degree onwards, and it will be 0 before 0.1 Z2 decade. Okay, next, when we have seen the zeros not at origin in previous slide. So here, when you have poles not at origin or real poles, in this case, for example, at P1. Okay, so the transfer function for this particular poles equal to 1 over S over P1 plus 1. Okay, so you have seen that when you have zeros at origin or not at origin, it will always a positive slope. But for poles, it will always be negative slope. Okay, so in this case, you have poles at P1. So you know that at P1, the line will be 0 from 0 up to that P1, and then from P1 onwards there will be decrement slope by 20 dB per decade. Okay, so if in zeros just now you have Z1, Z1, so it will be 0 until Z1 and then increment by 20 dB per decade. But for poles, you have 0 from 0 up to that P1 and then decrement line from P1 onwards by 20 dB per decade. And then for the phase of poles at P1, just as the zeros at Z1, at that particular frequency, it will be 45 degrees. But for poles, it is in negative values. Okay, negative 45 degree. And then you extend to earlier decade and extend another 45 degree to the next decade. Okay, and the rest will be 0. Okay, same goes to when you have the second poles. So if you have the second poles for the magnitude plot, so here is P2, so the line will be 0 from 0 to P2 and then decrement by 20 dB per decade at from P2 onwards. Okay, so this is for the magnitude plot. And for the phase plot, if you have P2, so at P2 it must be 45 degree, but for poles it is negative 45 degree. Okay, you mark that point first, and then don't forget to extend to earlier decade and next decade. So here is 0.1 P2 and here is 10 P2. Okay, so here is 0 and here is negative 90 degree, and don't forget to put constant lines before that and after that 90 degree point. Okay, so once you have all components, individual component being sketched, then finally you need to sum them up. So I'll show you an example later on to plot individual component, and lastly to sum them up to get your final frequency response of a specific transfer function. With that, I end this part. Thank you.